exactly. All right. So at any point, if things become confusing or get stuck, please, unmute yourself and tell me. All right. So density of state. We'll start with the simple concept of band, the conduction band and the valence band, like we discussed in the last lecture. And let me just get to the other slide to help, draw this in a better way. So we know that there are bands of energies in semiconductors that are allowed. So electrons can basically take up any energy, not just any, there are specific energy tags, as we discussed, energy states that the electrons can take up. So there is a range of energy in the conduction band and a range of energy in the valence band that the electrons can take up. Okay? And we basically, just for simplicity, we always try to draw them as flat lines instead of any other shape, just to simplify the discussion. So we'll have conduction band and valence band. When I just draw these two lines, remember that there will be a range. It's not just a line. There is a range of energy for, sorry, I just inverted it. So conduction band to the top. So starting from this minimum energy, going all the way up is your conduction band. And starting from this maximum energy and going all the way down is your valence band. Okay, so just keep that in mind. Now, let's get back to this slide again. Within that range of energy that is allowed in the conduction band or the valence band, there are some specific energy levels and energy states, as you know, as we discussed in the last lecture, that are allowed for the electrons to take up. And I kind of portrayed that as tags that the electrons can take up, right? And you have a limited number of tags available. Maybe say 2 tags here, 10 there, 20 there, and obviously these are random numbers. I'm just, trying to make a point here. There are a limited number of tags available for the electrons to take up. So these tags, in other way, is known as quantum states. Quantum states that we can assign to the electrons. And density of states is basically a measure of how many quantum states are available for the electrons to take up as you go down the valence band or go up the conduction band, okay? So apparently, simply because you are allowed to take up energies from this range doesn't mean you could just take up any energy. There are also allowed states within this range that the electrons can take up. So keeping that in mind, we'll have to calculate the density of allowed states in these two bands, in the conduction band, in the valence band. All right? And these functions that you see here, these mathematical expressions, they represent the number of quantum states available. C stands for conduction, V stands for valence. Okay, so in the conduction band and valence band. And typically we just express this as G without any loss of generality. So when I write GC, that represents the function that shows density of states in the conduction band. And GV shows the density of states in the valence band. All right, and we'll talk about these other details soon enough. But at the very beginning, we should understand the concept that there are densities of available quantum states in both conduction band and the valence band. And I'll explain, first of all, that we need to talk about what equilibrium is, and I'll talk about it in a second. But just let me know whether so far everything is good. Especially because of the technical situation that we are in. I just want to make sure you're all with me. Could anybody let me know that you could hear me well and you could see the illustrations that I drew? Please.
Yeah, I can hear you.
Okay, thank you. All right, so finally, let's talk about what equilibrium is. Imagine you have a semiconductor material and you haven't applied any voltage or electric field or magnetic field. So basically any sources of external stimulus. You haven't applied any of them. And obviously, I haven't mentioned this specifically, but I will. Temperature gradient, not just temperature gradient, they're together. And I'll explain why that is the case. So as long as you don't perturb the system externally with any type of stimuli, then we can say that the material or the system is in equilibrium. So a semiconductor is equilibrium means you don't have any external voltage or electric field or any other stimulus applied to it. And the reason why we just don't mention temperature, we mention temperature gradient, is because imagine you have a material here, you have temperature 1 and temperature 1, the same temperature in both sides. That's not a motivation for the electrons flow from one place to the other. The electrons will only flow if you create a difference in temperature, T1 versus T2. Imagine T2 is greater than T1. So particles will try to move away from high energy or high temperature zone to low temperature zone, typically, to minimize their energy. Only then there will be a motivation for them to move. Otherwise, if you have same temperature everywhere, there is no motivation. It's not a stimulus in that case. Okay, so that's why we talk about temperature gradient or difference in temperature, not just temperature. All right. So now that you know what equilibrium means, let's see how the density of quantum states look like at equilibrium. So these lines that you see here, they represent this function, GCE, and this line represents DVE. So basically, if you take this mathematical function and plot it, you'll have a shape like this, okay? Which illustrates that the density of quantum state gradually increases as you go higher up in energy in the conduction band. So in the towards the bottom of the conduction band, you have less quantum states available. And as you go up in energy, there are more and more available quantum states. That means, obviously, if I ask you, in your opinion, where will the electrons be most comfortable to be in the conduction band? The answer should be, they should be most comfortable staying close to the minima, because the lower energy you have, the better off you are. Obviously, good things come in limited supply. So the quantum states available closer to the minima of conduction band will be in short supply compared to the ones that you get as you go higher up in energy. Okay, unfortunately, but it is what it is, and we could easily derive this expression, and it's also available in the textbook that I follow, Niemann. You don't necessarily need to go over it, but you can if you're interested, and I'll be happy to discuss the details if you're interested. But ignoring that part, let's just take it as a given that we somehow know that this equation represents the density of quantum states in the conduction band. And if you just plot it, it will look something like this, which illustrates increase in quantum states as you go up in energy. And quite opposite for the valence band. As you go down in energy in the valence band, you have more and more quantum states available. So that has some interesting significance, and we'll talk about it in a second. Now, as you see, there are no quantum states available in this zone because it's a forbidden energy band. As you might remember, there is a band gap here between conduction and valence band. So there are no quantum states available in between ECE and EV at all. Now, keeping that in mind, so familiarize yourself with these two notation. This will be used over and over again throughout the lecture and throughout the course, in fact. So one more thing, if you have more quantum states available in a certain band, that represents you can accommodate more electrons. So the more states, possibly you could accommodate more electrons, but that doesn't necessarily mean you have more electrons. Okay? These are states available for the electrons to take up, but you have to also supply those electrons so that they could take up that state at some point. So now that takes me to the next concept, which I will get to in a second, but okay, let's fast forward to that concept and we'll get back to the math problem in a few minutes. So the concept is Fermi-Dirac probability function, which essentially represents the probability that a quantum states will be occupied by an electron. Remember my last comment, simply because you have a quantum state doesn't mean that state will be occupied by an electron, right? There is a probability that an electron might take up that space, or it might take up a different state, or it may not even be there. So that state could be empty. There are all sorts of possibilities like this, right? So we have to measure the probability or possibility of a quantum state being taken up by an electron. And I'm assuming that you have some background in probability from your high school, but if not, it's okay. It's not really, too much deep into the probability here. The way we define that probability would be by the number of electrons available in the system and the ratio between the number of electron and the number of quantum state available, right? Let me just use a simple analogy for here. Imagine in a system you have 3 red balls and 4 blue balls. Okay. Now, if I asked you, if you randomly pick a ball, what is the probability that the ball would be blue? Then you should say, based on your high school probability lessons, that there are 4 blue balls available, and the total number of balls would be 3 plus 4, that is 7. So the probability that the random pick would be a blue ball would be 4 over 7, right? A similar concept. So here, your total number of available states would be G of E, and total number of electrons that are available in the system is N. So N over E would be the probability that a system, a quantum state. So this is the probability of a quantum state being filled with electrons. And this probability function, which is a very simple concept, as I could just explain with a very simple high school probability analogy, this function is called the Fermi-Dirac probability function. And if you see me write f of f, that represents Fermi function. F stands for Fermi function, all right? And it's a function of energy, because as you see, quantum states are dependent on energy. The higher the energy is, different kinds of density of states you can have. So this function is represented using this exponent. And I'm just gonna throw it out there without providing too much context, as you can see. As we move forward later in the lecture, we will lose most of the maths, and we will just talk about the end product of those maths, and we'll be using those maths to make a point, as you probably must have experienced already in the course. So the Fermi probability function is in this format, which represents the probability of a quantum states being occupied by an electron. Now, let me go back to the math problem that I skipped, which will hopefully help us see how we could use some of these functions. So the problem states, determine the number, and the number in terms of number per unit volume or per centimeter cube. Determine the number of quantum states in silicon between 2 energy levels, as you see here. And the energy levels are EC, between EC and EC plus KT. By the way, K is Boltzmann constant, T is temperature. And as I told you, KT over Q is a measure of thermal energy. I think I mentioned that in one of the previous lectures. But when the charge is the charge of electron, we often just write it as KT, because we measure this in terms of electron volt. When you're measuring energy in terms of electron volt, you don't need to just do this, KT over E. You can just mention it as KT, all right? So EC plus KT is a measure of energy, and EC is obviously the energy. And by the way, what is EC? Just to rephrase that again. EC is the minimum of conduction band. EV is the maximum of valence band. There will be energies down below and higher up in the conduction band, just as a recap. Okay, now we have to find the quantum states within EC and EC plus KT. Where is that? This is, let me change the color here. In here, in this zone, starting from EC and EC plus some other energy. So EC plus KT. So we should be looking at the expression for quantum state in the conduction band, not the valence band, okay? So let's start with this equation, which you saw in the previous slide here. So we'll pick this equation, not the other one. Let's see what we do not know. Do we know the energy? So basically, okay, let's first see what we do know, and then we'll talk about what we do not know. You know the value of pi, you know the value of Planck's constant, which is h here. And this Mn star that you notice here, which I didn't explain in the previous slide, is the effective mass of electron in silicon. And if you review the last lecture, we talked about the concept of effective mass. Effective mass is basically experimentally measured. There is an effective mass of electron in silicon. We all know the mass of electron, which is 9.1110 raised to minus 31 kilograms. But that doesn't mean it's going to be the effective mass of electron everywhere. If the electron is in silicon, it has an effective mass for silicon. If it is in germanium, it has a different effective mass. If it is in gallium arsenide, it has a different effective mass. Okay? And we typically measure them experimentally. So we assume that you could just Google it and find the effective mass of electron in silicon. And for all practical purposes, for example, if it is an exam question, I'll provide you with this number. You don't need to memorize this or anything, okay? All right, so Mn star is given. we assume that it's given, or we could find it from Google. H and everything else is known. The only thing that you need to worry about is this portion, which I will show you now. So how do you calculate the number? Remember, GC is not the number, it's the density. So GC represents the number of quantum states per unit energy per unit volume. So it's a double density, basically. Density in terms of energy, density in terms of volume. So the unit of GC is number per centimeter cube or meter cube, whatever the unit of volume you want to use, per electron volt, which is basically electron volt is the energy unit here. Or you could use joule, but typically in semiconductor physics, we use electron volt to measure energy. And all of these are mentioned in the previous slide, which I didn't talk about because I wanted to cover that with the math here. You notice that? So the unit of GCE or GVE are both number per centimeter cube. So by the way, this should be centimeter cube because I've already used division here. Per centimeter cube per electron volt. All right. So number per centimeter cube per electron volt, same for the other one, GV. Now, to calculate the total number, you need to integrate this density, which is GCE, with respect to energy. And the limit of integration should be from the lower point of energy to the upper point of energy, EC plus KT. All right. So this is your GCE, as you notice here. And we are going to integrate that within this zone that was mentioned in the problem. And that's exactly what we're gonna do. And again, I keep telling you, this is not a math course, so I'm gonna quickly skip over the math steps and get to the point eventually. You don't necessarily need to worry about the math step for the sake of this particular course, but I do encourage you, obviously, reviewing this whenever it's possible at your leisure. So after you go and do the math and complete the integration, you could put in all these numbers, which are all given, and you get a number. So this number shows you how many quantum states are available. And now we can be a little bit more realistic. In terms of examples, I mentioned that, say you have 2 states, 20 states, 30 states. I've been using numbers like this. But this is a more realistic number to show you how many quantum states are available in a material. It's 10 raised to 19. See, it's a huge number, right? It's billions, and basically, as you can see, billion kind of situation here. So there are a lot of quantum states available in a material, and this is just in the conduction band. And there are similar number of states available in the valence band, by the way. So we are dealing with a lot of quantum possibilities, but don't get it wrong. Simply because you have 10 raised to 19 quantum states doesn't mean you have 10 raised to 19 electrons. Not all of these quantum states will be filled with electrons. There are possibilities for the electrons to take up, but the electrons will take up some of them, not all of them. Keep that in mind. And one more thing to mention, this concept of density of quantum state and density of quantum state in conduction band and valence band. Just to remind you that we are looking at single crystal material. And the reason why we have a band of energy was because the material was in a crystal. So you have atoms that are all together in a crystal-like setting in a 3D environment. Okay. So that's what led to the band structure all on a sudden. And we had a detailed discussion about why bands occur. When 2 atoms come, 1 energy level is split into 2. When 3 atoms come, it gets split into 3. And when you have multiple atoms, you have, more splitting, and you get a band of energy instead of just 1 energy level, right? That's how the bands come into being. So all of these concepts are applicable to a crystal. And in a crystal, you don't have 1 electron or 2 electrons. You have billions and trillions of electrons because there are billions of atoms as well. So keep that in mind. I just want to make sure that you get the right picture, not assume something in the middle. All right. So are we good so far up to this point of Fermi function? Please ask questions if you have any. And I recommend that you could unmute yourself or maybe just quickly go and check the, you know, chat, Zoom chat, and make sure that, okay, all good. Thank you. All right, so looks like you guys are okay. All right, so let's get back to this discussion again. So in terms of the Fermi-Dirac probability function, I just showed you that there is an exponential, relationship between energy and temperature and whatnot. But there is one aspect that I didn't cover intentionally, which I will talk about now. There was one parameter marked as EF, which is called the Fermi energy, which I didn't talk about before, and I will talk about in the next class. Not class, next slide. Okay, so Fermi function represents the probability that an energy state or quantum state will be filled with electron. And this function is dependent on a parameter called the Fermi energy. So it must be something interesting and important. And that's exactly what we're going to find out here in this slide. Let's talk about it. Imagine in a system, in a material system, you have different levels of energy that are available for the electrons to take up. And within every level, you have different number of quantum states. And this is just an illustration, obviously. It doesn't mean that you have 2 or 4 states, right? Just an illustration. So you have a certain number of states available for the electrons to take up, like buckets that the electrons can sit in. So imagine in a material, all of these states are taken up to a certain level. So all of the energy levels up to E4 have been taken up, and all the energy states above it are empty. So you have a situation like this, and we are looking at absolutely zero temperature, T equals 0 Kelvin, which is a hypothetical temperature, as you know. So at that temperature, I could mark a boundary here. I could mark a boundary below which all the energy states are filled, all the quantum states are filled, and above which all the quantum states are empty. Okay, so this boundary, which I can mark as EF, is known as Fermi energy level, which is the boundary between quantum states that are completely filled and quantum states that are completely empty. All right, and let me use this graph, this diagram, to represent this situation. Imagine this is our Fermi function, EF. Notice the axis here. This is an energy axis. And in the y-axis, you have the Fermi probability function. What does the Fermi probability function represent? It represents the probability that a quantum state will be filled with electron. Okay. Now, I wish I was in person in the class and I could have listened to your responses, but I assume that some of you could at least tell me an answer here. Imagine let me just get to an empty slide. So this x-axis is energy. In the y-axis, I have Fermi function, which is a probability that an energy states or quantum states will be filled with electron. Now tell me, if this is my Fermi energy, what is the probability that an electron will be in a quantum state? Like a quantum state below Fermi function will be filled with electron. What is the probability below EF? Can anybody tell me? I know it's difficult to kind of respond over Zoom, but so I'm going to answer for you for now. So according to the definition of Fermi function, any energy below Fermi function, any quantum states will be filled with electron. So it's absolutely certain that we'll have a quantum state that's filled with electron below the Fermi function. And for absolute certainty, the probability is 100% or 1. Okay, so there is a probability of 1 that a quantum states below the Fermi function will be filled with electron. And what is the probability that above the Fermi function, a quantum state will be filled with electron? And if you correlate that with this diagram that we just saw, all the energy levels above Fermi function, energy level will be empty, right? So what is the probability that it will be filled with electron? 0. It's improbable, right? So basically, above the Fermi function, the probability of filling a quantum state with the electron will be 0. Below it, it's 100%. So there is an abrupt shift from 1 to 0. And remember, all of these are happening at T equals 0 Kelvin, absolute zero temperature. And we haven't even talked about non-zero situation yet. We will talk about it in a second. But I hope that makes sense. Now let's get back to this slide and talk about this diagram. Shows absolutely 100% possibility that a quantum state will be filled with electrons below the Fermi function, and a quantum state will be devoid of electron. Sorry, and zero probability that a quantum state will be filled with electron above the Fermi function. Okay? And all of these are at T equals 0 Kelvin. Now, let's see what happens when the temperature is non-zero. It's greater than 0 Kelvin, right? And that's when electrons start getting energy and try to get up to the upper level and fill up some quantum states there. Okay, you see that? So electrons some of the electrons, not all of them, will start getting to the upper layer and start filling up some quantum states above. This was the Fermi level, by the way. This was the Fermi level. So electrons are getting above the Fermi level and filling up some quantum states as you increase the temperature. Remember one more thing, and that's why I emphasized the temperature gradient in the previous slides. We have increased the temperature, but the same temperature is applied to the entirety of the material. All the different portions of the material has the exact same temperature. There is no gradient. So it is still thermal equilibrium. We are just increasing the overall temperature of the entire system. There is no gradient. Remember that. Okay. So now, can I say that even above Fermi level, there will be some quantum states that will be filled with electron. So there is a possibility that a quantum state will be filled with electron even above the Fermi level, right? In terms of mathematical representation or geometric representation, graphical representation, I could say that even above the Fermi level, there is a non-zero probability of finding an electron in a quantum state. And by the way, when the electrons are getting away from the states below the Fermi level, there will be some quantum state that will now become empty, which were previously filled for sure. Now they have a zero temperature. There is no longer a guarantee that a state below Fermi level will definitely be filled with electrons, because maybe the electron has moved to the upper level. So there is a probability, and that's exactly what I'm gonna draw right now. Closer to the Fermi level, there is a probability that you may not find an electron filling up a quantum state, and even an electron could be found filling up a quantum state above the Fermi energy. So basically, whatever electron you missed here will show up to the other side. And that will happen closer to the Fermi level. Here is why, because the electrons closest to this energy level will probably be the first ones to migrate to the top level, not the ones down below, right? That's logical. The ones that are, easiest to put to the other level will get to the other level first. So in terms of, let me just get back here. I think this diagram shows you that. So in terms of the graphical representation, we could have a smooth transition from abrupt 1 to 0 transition to a smoother transition from 1 to 0 at absolute zero, at non-zero temperature. Now, I want to also show you what happens when you increase the temperature even further. Let me draw the first temperature here, T equals T1, which smoothed out the transition a little bit. This is the first case. For the second case, when you increase the temperature even further, what happens then? Then electrons from underlying states could also start going. So you empty more of the quantum states that are below the Fermi level and populate more of the quantum states that are above the Fermi level, right? So that's exactly what you see here. More of the quantum states below the Fermi level have less probability of getting filled, and more of the energy states above the Fermi level are probably going to be filled again. You see, the probability is enhancing. So now, getting back to the drawing board again, if I ask you to do it yourself without looking at the diagram, just to draw it from scratch, let's do that again. Energy Fermi function. I'm going to plot it. At absolute zero temperature, the probability is like this. This is your Fermi function. You have 1 and 0. So below the Fermi function, there is 100% guarantee that you have a quantum state filled with electron. Above the Fermi function, oh, sorry. Yeah, above the Fermi function, there's absolutely no chance of getting an electron filling a quantum state. And this is all for absolute 0 Kelvin temperature, okay? Now, if I tell you that you have, say, 250 Kelvin temperature and 500 Kelvin temperature, I'm just picking two numbers here, 250 Kelvin and 500 Kelvin, which are obviously above 0 Kelvin. So let's start with 250 Kelvin. For 250 Kelvin, maybe you have a situation like this where some electrons will move over from the energy states below Fermi energy to states above Fermi energy, okay? So maybe this is 250 Kelvin. So for 500 Kelvin, it'll be even more severe. You have a situation like this, and you'll fill up more and more energy states above the Fermi energy. I hope that makes sense. This is 500 Kelvin, okay? And I want you to notice something interesting that I did. It is, see, all the graphs are going through one common point. I didn't just randomly draw it. I deliberately made them go through a common point here. And I'll explain the reason behind it in a second. But without this common point, are you okay with everything else that I covered? Let me quickly go back and check and see if there is any comment on the Zoom chat. Okay, yes, thank you. Thank you. All right. Okay, perfect. So let's go back to this one again. What did I do? Okay, I meant to go to the slides. Okay, sure. Now, let's talk about that point. It must be something really important that all the graphs are going through the same point for some reason. Even at absolute 0, you still go through that point. And that point represents half probability, like 50% probability, as you see, half. So it's important, right? And I'm going to explain that to you right now. Let's see. At energies below Fermi energy, at absolute 0 temperature, there was a 100% probability of finding an electron filling up an energy state. At energies that was above the Fermi energy, there was 0 probability of finding an electron filling up a quantum state. But the question is, which you didn't ask me, but maybe it should have come to our mind, exactly at Fermi level, will we have 100% probability or 0 probability? What should happen? There was an abrupt shift there, right? We don't know between 1 and 0 whether or not we'll have 0 here or 1 here exactly at the Fermi energy level. So let's try to see that mathematically. So this is the Fermi function. If you put in energy equals EF, which is the Fermi energy, what happens there? This EF and EF will cancel each other out. So you have 0 here on the numerator. So what is exponent of 0? So you see that here mathematically, basically. So by putting E equals EF, you get this one, exponent of 0. Anything to the power 0 is 1, as you know. So this would be 1. So you have 1 plus 1 plus half. So basically at absolute 0 temperature, at Fermi energy level, you have 50% probability that an quantum state exactly at Fermi energy will be filled or empty, right? There is a 50-50 chance. So that's why when the temperature is absolutely 0, let's see what happens there. Notice that if the temperature is not 0, it doesn't matter what the temperature is. If the temperature is 500 or 600 or 700, doesn't matter. Doesn't matter what it is. The moment you put in energy equals Fermi energy, the numerator becomes 0 and nothing else matters. So everything becomes simple, half, as you know. However, what happens exactly at absolute 0 temperature? Exactly at absolute 0. Okay, so let's see. If you put in T equals absolute 0 and you have energy equals Fermi energy, now you have a problem. You have 0 over 0, right? You see, it's kind of indefinite formulation. So that's why you don't have to worry about it because absolute 0 temperature doesn't really exist. I mean, this is theoretical, obviously, but at absolute 0, you have a indefinite situation, like undefined situation, basically. But other than that, for any other temperature, you have a answer. Like all of this will have a 50% probability of filling up a quantum state at Fermi energy level. So that's why everything goes through this point half. But for absolute zero, we basically don't even draw that line. We just typically, we would just ideally draw this line and the other line. And there will be a discontinuity in between. Or sometimes you'll see a dashed line just showing that there is a transition. But we don't necessarily mean that it will be like going through this path, okay? I guess all with me so far? And the concept of Fermi energy is extremely important because moving forward in most lectures, diode, BJT, MOSFET, you name it, we'll be using Fermi energy level over and over and over again. So it's extremely important that you understand Fermi energy level. And I do appreciate the fact that you are doing it online and there were some technical difficulties. So it must be difficult for you to get it properly. So please give it some thought and, I'll be back soon. If you have any confusion or questions, please don't hesitate to use up my time as much as you need to make sure you understand this properly, okay? Quiz yourself, we'll go over this over and over again. Try to explain this to your friends in a way that, when you try to explain something to other people, only then you realize whether or not you really understand something, okay? So do that. Now, let's move to the next concept for the interest of time. Before moving into the next concept, I typically try to use a simple math question to try to see whether we could use it from an engineering sense. So this is a math question that let's try to solve it together. So at 300 Kelvin temperature, determine the probability that an energy level 3 kT above the Fermi energy is occupied by an electron. So which function helps us calculate the probability of a quantum state getting filled? Well, the famous Fermi function. So I need to write the Fermi function here. And you definitely remember, this was the expression for Fermi function that we saw. 1 over 1 plus exponent E minus EF over KT. As simple as that, okay? And let me just bring it up here. Notice 3 KT. What is 3 KT? This is basically an energy. Get used to the term KT because this will keep coming up over and over again in semiconductor textbooks. KT basically represents energy at temperature T. Simple. K is Boltzmann constant. So 3 KT is basically 3 times KT. That's all. Just a measure of energy. Now, so basically, what is the energy of the level that we are after? The energy of that level that we're trying to look into is 3 KT above the Fermi energy. So can I write that it is Fermi energy plus 3 KT? That's what this section means. The energy is of that particular level is 3 KT above the Fermi energy. So basically, it is like EF plus 3 KT. Okay, so I'm gonna replace that quantity here in place of E. And as you can see, there is already an EF sitting in here. So this will be cancelled and you end up with 3 KT. So basically this will be 3 KT. I hope that makes sense. And essentially just to simplify the calculation, this KT and KT will be cancelled and all you are left with is just pure number. So you get a number, which is like 4%. So there is a 4% possibility that a state is occupied by an electron. Simple. That's how we use the Fermi function to calculate the probability. All right. Now, let's move to the next slide where we talk about an inverse Fermi function. Before I explain that, I think it will be better to take an analogy, a simple analogy. Imagine if I ask you that if you throw a dice which has 6 sides, give me a second. Okay, so from 1, 2, 3, 4, 5, 6, you have 6 numbers. If I ask you that if you throw a dice, what's the probability that you get 2, say? So the probability would be, it would be ideal to ask you and see your responses, but I'm going to answer for you. 2 is just one quantity and you have 6 possibilities. So the total number of possibilities will be 6. And the possibility that you are after is just one option. So there is a 1/6 probability that when you throw a dice, you get a 2. Okay. So if I ask you, what is the probability that you will not get 2? You will not get 2. So what are the options without 2? So you have 5 other options. we could write it as 5/6. That is the probability that you will not get a 2. However, I could have done it in a very different way. So the probability of getting 2, this is the probability of getting 2, which is 1/6. Now, the probability of not getting 2 will be basically 1, which is 100% probability. 1 represents 100%, obvious situation, minus probability of getting 2. Okay, as simple as that. So if I ask you, what is the probability of, folks, can you still see my screen? I hope so. Okay. If not, please speak up. So the point is, if I ask you, say, what is the probability of you passing an exam? You tell me that it's 50%. And what is the probability of you not passing an exam? 1 minus 50%. So 100% minus 50%. So basically 50% again. So that's a simple way to get inverse probability per se. So similarly, what is the probability of an energy at a given state is filled with electron? That's represented by Fermi function, as we have just seen before. But what is the probability that an energy level is empty? Basically, empty means not filled. So it will be as simple as 1 minus the Fermi probability function. As simple as that. So you just take 1 minus, put in the Fermi function, and you calculate something, you get something else. But why do we care about this specifically? I mean, it would be fun to ask you and see your responses, but again, to answer for you, because wherever we see that there is a missing electron or a state is empty, we could treat it like a hole. And we talked about the concept of electron and hole. So basically, we are looking at the probability that a quantum state is filled with hole. So what does a state being filled with hole mean? It means there is no electron at that quantum state. It's simply a different way of putting the same concept. All right. So if this is the Fermi function, which you have seen before, if you plot 1 minus Fermi function, it looks exactly like flipped, as you see. A mirror image kind of thing. It's not exactly mirror image, but you get the point, right? This is Fermi function. This is 1 minus Fermi function. This represents probability that a quantum state is filled with electron. The other one represents the probability of quantum state being filled with holes. Okay, let's see this simple math question. Assume that the Fermi energy level for a particular material is 6.25 electron volt. So that means they have given us EF, basically. Calculate the temperature at which there is a 1% probability that a state this much above, this much below the Fermi energy will not contain an electron. Okay, so let's see. This is not asking to calculate the energy level to contain an electron. It's asking the probability of that state not contain an electron. So we are not after Fermi energy, we're after 1 minus Fermi energy. So we should look at this equation. It's asking for this quantity, 1 minus Fermi function. It's asking for this value. And that's exactly what we're going to calculate right now. So just put in all this information. You know the Fermi function. They've given you the Fermi function. This is 6.25. And the energy state is 0.3 electron volt below the Fermi function. So what is the energy level? Fermi function minus 0.3. So the Fermi function was 6.25 electron volt minus 0.3. You get whatever amount of electron volt. Just put that number here. Calculate. You know the temperature as well, which is oh no, you have to calculate the temperature. They're asking for the temperature. Basically, you put in all this information. They have already given you the probability that the state will not contain an electron, and which is 1%. 1% means 0.01. So they have given you this value completely. So you put in all this information, you calculate T out of it, and it is what you get. Okay. And also, I just want to highlight that they could have asked you, instead of an energy level not contain an electron, they could have asked you that at this energy level, there will be a hole. So it's all the same. Will not contain an electron is same as saying there will be a hole. Okay. So keep that in mind. That's the reason why we use this reverse Fermi function to help with calculating holes. All right. Let's get to the next slide and talk about Maxwell-Boltzmann approximation. Often we just mention this as Boltzmann approximation. And let me explain what that is. So this is the Fermi function. This is a Fermi function, and this is how it looks like when you plot it, mathematically plot it, okay, in a graph, say. Now, notice if the energy that the particle has is greater than the Fermi energy, especially much greater than the Fermi energy, then the numerator and the overall quantity inside the exponent will be, a larger value. And when you have, say, exponent 2, exponent 3, exponent 4, this becomes a large quantity. Okay? It's much larger than 1. So you can kind of ignore 1 with respect to the companion inside the exponent. Remember that. So then if I ignore 1, this becomes further simplified, and you could just take, imagine you have e power x, you could just write it as e power minus x. That's exactly what you're writing here. Just ignore this 1, and this equation becomes further simplified. And that's an approximation that Boltzmann did, and that's why when you plot this exponential function, you get this blue dash lines that you see. So it matches with the Fermi-Dirac function, which is a more complicated function, but it goes, in a completely different direction if you go towards lower energy. So it's not really meant for lower energy. Why? Because then this concept that this is much more greater than 1, sorry, I meant to say this exponent is much more greater than 1, will no longer hold, because if the energy is less than Fermi energy, this is going to be an exponent to the power minus 2. So it will be essentially much lower than 1. So this will be less than 1 in that case. So you can no longer make the assumption that 1 is negligible, right? So that's why this is only valid for energy that is far, far greater than the Fermi energy. So in this zone, only this zone, this will be valid. Not as you get close to the Fermi energy or go below the Fermi energy. Then you can no longer make this approximation. And here is why we care about it. Once you make this approximation, that means you are basically dealing with here in this zone. Typically, that's where most of our interesting things occur, because electrons go to the conduction band, exceeding the Fermi energy, and they typically reside here in this zone. So we could just do fine with Boltzmann approximation. And the real reason behind making this approximation is not just to, fit a graph. It's because if you use actual Fermi function, many of the mathematical calculations that we will encounter, in the upcoming slides will be, it will be necessary for us to use software to calculate in a numerical way. We couldn't do hand calculation. We couldn't analytically calculate those things. So to simplify the math, folks decided to use Boltzmann approximation, especially for the situation that is far, far above, energy is far, far above the Fermi energy level, right? Maybe if you don't care about hand calculations anymore, you just care about software simulation. Sure, just go ahead and use the Fermi function. And you'll see the integrations and derivatives will be more difficult to handle. Mostly integrations will be very difficult to handle, but you can still do it using a computer. But for hand calculation, that's not an option. I hope that makes sense. For all the equations that you'll see in the upcoming slides, and possibly throughout the lecture, throughout the course per se, we'll be simplifying all these equations using Boltzmann approximation. So it's important for us to understand where that holds and where that fails. It's not a universal approximation that works everywhere. It only works whenever the energy of the zone that you're interested in is much greater than the Fermi energy level. Just keep that in mind. Okay, now, so far we have looked at the density of quantum states. We have looked at the probability that those quantum states will be filled with electron, or the probability that those quantum states will be empty, right? So we have seen both those probabilities. At this stage, we'll start looking at how many electrons are there and how many holes are there. We're going to start calculating exactly how many electrons, because that's the most important thing, right? You don't just care about the possibilities of electrons being there, or you don't just care about, availability of quantum states, because if there is no electron, that quantum state is not going to do anything for you. So you need to see exactly the number of electrons that you are going to get. And this is the slide that will help us understand that. See, there is still some math in this course, and these maths are essential, so don't ignore them. It's not like the chronic penny model that I talked about in the last class. And I told you that if you don't like it, you can ignore it, but not for this one. So if you are feeling lost, it's okay. We all feel lost at some point. So please make sure when I'm back, hopefully, in Knoxville, please make sure to get me in my office or my office hours or whenever is convenient for you, and ask me questions and make sure you understand this fully, properly. And I'll also try to post the recording. I hope it will come out okay, given the technical difficulties, but we'll see how that goes. All right, so now notice that in this equation, which I'll explain shortly what it is, you are basically multiplying two functions that we have talked about so far, density of state function and the Fermi function. Okay? So to explain that, I will go back to the drawing board again and ask you, like, use an analogy. Imagine you have a, say, 30% probability of winning the lottery. Say, okay, I'm just giving you a 30% probability of winning the lottery. Now, if I ask you, if you buy lottery tickets, how many times can you win? Probability represents that you cannot win every time. There is a probability that you might win, but there is also a probability that you may not, right? So the more number of tickets you get, say hundreds, thousands, or whatever, the more number of tickets you buy, the more chances of you actually winning. Okay, so the total number times total numbers that you buy and the probability count will give you the actual number of winning, as you can see. So similarly, imagine you have a system with X, or sorry, GC, number of quantum states available, but not all of them will be filled with electrons. Okay? Right? So imagine you have a system with GC number of quantum states, like your lottery ticket. You may win, you may not win. Similarly, it may be filled, it may not be filled. Okay, so just see the analogy. And what is the probability of winning lottery or having an electron filling your states? That was Fermi function. That's the probability that a quantum state might be filled within an electron. So if you multiply this two, you get the total number, an approximate total number of how many winning you can get, or that means how many electrons you can actually have in your system. So the total number of places that the electron can take up times the probability that an electron will even take up a energy state. These two, the product of these two will give you an approximate number of electrons that you can possibly get in a system. And even then, with probability, it's never certain. Simply because you have a 30% probability of winning a lottery doesn't mean if you buy 100 tickets, you will exactly win 30 lotteries, as you can appreciate, right? There is a probability. It gives you a sense of the average count, but it may not be exactly what you get eventually, right? So similarly, in semiconductor physics, we deal with quantum mechanics a lot. So we deal with probability, and that's why these numbers are all approximation or estimates. They may not be exactly what you get eventually, but they help you make interesting decisions. Okay, so this quantity represents the number of electrons you get in the system. Now, this figure basically represents this mathematically. So let me explain that. Please follow along as I draw things. So this is the GCE function that we saw before, and this is the Fermi function that we saw before. And notice this is a little bit flipped view because this is the energy axis, by the way, okay? And this is the Fermi probability function axis. So it's basically flipped, as if you have rotated the axis, y-axis in x direction, x-axis in y direction, basically. Why? To match up with the axis of the density of state function, which was energy in this direction. So just to match up these two functions properly. Now, when you multiply these two, just notice this is one of the functions, and this is the other function. When you multiply these two, whenever one of them is 0, which is the red one here, you get 0. And when both of them are non-zero, you get some number. And again, at this point, the Fermi function becomes 0 again. So your total product becomes 0 again. Doesn't matter. GC is increasing quite a lot, but your Fermi function is 0. So you don't have any chance of getting any electron there. You see, it's basically purely mathematical. You just take these two functions, multiply them together, and you get a shape like this. Simple. So that means this is an estimate of the actual number of electrons that you get. So you get more electrons here and absolutely no electrons higher up in the energy. Isn't that, what we expect? Typically more electrons closer to the minimum energy level. And as you go higher up, there is less and less electron and almost none as you go too high in the energy. Okay. I hope that makes sense. And by the way, and this is a simplification, this is a simple representation. The real way to get the number would be to actually integrate, because remember, GCE is not the number of states. This is a misconception. GCE is not the number of states, it's the density of state. It's density meaning number of state per unit energy, per unit volume, right? So if you want to get the total count, you have to integrate it. So that's why we are basically integrated with respect to energy, because it's an energy density. So meaning if you want to get the count between energy 1 and energy 2, you have to integrate it between energy 1 and energy 2. Simple. So this product will need to be integrated because it was a density. I hope that makes sense. And similarly, I could talk about the exact same thing for the valence band. For the valence band, notice we are doing something interesting. Just compare that with this electron expression. For electron expression, this was the probability of, sorry, this was the density of state. This was the probability that state will be filled with electron. For valence band, which is here, we'll be dealing with electrons being gone to the other band. So basically there will be voids, which are also known as holes, as you remember, right? So we'll be dealing with a hole possibly taking up a quantum state, not electrons. So what is the probability function that represents a hole occupying a state? As I discussed before, 1 minus Fermi function. This is the total number of state. This is the probability that state will be filled with holes. So if you multiply them together, you get the total number of holes in the valence band, not total number of electron. Remember, you get the total number of holes. Okay. So, and similar concept, you also have to integrate it. Meaning, if you want to go from this energy E1 to E2, you have to integrate it, from E1 to E2. Simple. Okay. So mathematically, you might have to flip it from E2 to E1, but doesn't matter. It's all mathematics. You get the same number, by the way. So apparently, this number represents the total number of electrons available in 0, and this number represents total number of hole available, P0. Why 0? 0 represents thermal equilibrium. In semiconductor textbooks, whenever you see 0 written up with any quantity, that represents a thermal equilibrium. Okay, remember that. Or by the way, let me take that back. Not necessarily just thermal equilibrium, just equilibrium, any equilibrium. Okay, but many textbooks will use the term thermal equilibrium, which is essentially the same thing. So either equilibrium or thermal equilibrium, we represent these quantities with 0, N0 and P0. And we will see soon enough what happens when you are not in equilibrium, right? We'll talk about it in the next lecture or so. All right. And by the way, as you might remember from your high school integration class or maybe other integration classes, that an integration is nothing but the area under the curve, right? So that's what this textbook mentions. If you take the area under this curve, you get the total number of electrons. But don't worry about the area. Basically, you are integrating anyways. You are mathematically going to get the number. I just wanted to explain in case you get confused later on reading this. What does it mean? Area is nothing but the integration of this quantity. Okay. Now, we'll try to end with this slide, and I want to show you the thermal equilibrium concentration of electrons and holes and how we get these numbers. So we have just talked about how this represents the total number of electrons, right, in this slide and this slide. But we haven't seen how the expressions look like when you go through the integration. That's what I'm going to show you here. So here, notice this equation. This is nothing but GC, which we saw in the first slide. Let me just quickly go back and show you the first slide. This was in the first slide. And remember, there was an expression for GVE in the first slide as well. So you get it there. There was an expression for the Fermi function as well. Expression for the Fermi function, okay? So let me just go back here and where is it? It is here. So you replace this GCE and you replace the Fermi function with the actual expression. I would have asked you a question here, but I'm going to answer for you anyways. Why does it look this way? Because we have used Boltzmann approximation. Okay, that's why it's so simple. Otherwise, it could have been 1 over 1 plus exponent of something. Okay, and then it would be non-integrable, by the way. Then you couldn't just analytically integrate this. You have to use a numerical approach and computers to simulate, basically calculate. But using Boltzmann approximation, you make it simple. You could even hand integrate it. It's there. All the steps are there in the Niemann's book if you are curious. But regardless, if you go through the steps of integration, you get an expression like this. And I'll talk about it in a second, but let me also address the limits of integration. So let me go back here and tell you our limits of interest. We should start with the minimum energy in the conduction band, which is EC, and go all the way up to infinity, because we don't know where to end, basically. We want to see all the electrons available in the conduction band. Okay? And that's what you see here. Starting from EC, going up all the way to infinity. We want to get all the electrons that are available in the conduction band. So this is the number of electrons available in the conduction band. Simple. Okay, so what is NC? This is just a, apparently this N0 had a complicated term sitting in there. We just replaced it with another constant. We named it NC. C basically stands for conduction band, and N is basically just a number that we are using. And just visualize this in a way that you have this complicated quantities sitting in here. Simple, okay? And we just replace this as NC. That's what the textbook does. I want to show you what shows up in the total equation. You have Mn star, which is the effective mass of electron. You have temperature, you have Planck's constant, you have minimum of conduction band, you have the Fermi energy. You see, Fermi energy level will show up every time. So that's how you get it. You do the same steps to calculate the whole number of holes using this expression, and you end up with a similar equation. Kind of interestingly, in most cases, equations for electrons and equations for hole will be similar. But instead of NC, which C stands for conduction, we'll be using NV, V stands for valence. And we have MP star, which represents the effective mass for holes, not for electrons, because we are dealing with holes here. Okay, so we'll stop here in this slide, and basically these equations could be used moving forward in the next set of slides that we'll see in the next class. So thanks again for your flexibility, and sorry about all this technical difficulties. I'll try to do better in the next class, Thursday's class. I'll try to take the call from my hotel room instead of the lobby. All right, so I appreciate your patience and understanding. Take care, everybody.